So, today, lecture number 14, we're talking about game cameras and views. So, visualizing games. Up until now, all of our games, well, assignment 3 changes this, but in assignment 1 and assignment 2, there was kind of this 1-to-1 ratio between the game world, right? The pixels in which you are, like the XY coordinate of the thing that lives in the game world, and where that thing is actually on the screen. There was no difference between those two things. But in reality, video game worlds are often much bigger than we can display on the screen at once. Like, who's ever played a video game where the entire game world was on the screen, right? That basically only happened in the old arcade days where it was like Pac-Man or something like that. And so, like the real world, we can only display a subsection of the world at a given time. And so just like you're walking around and you can only see like sort of this part of the actual environment, because that's how eyes work, in a game you basically have eyes as well, and you're looking typically at some sub-portion of that world. And the part of the world that we can see is called a view. And so this is the SFML term for it. Other game engines may have a different term for it, but you would just use the equivalent implementation in another game engine. Also, a lot of systems call it the camera, but because we're in 2D, we call it a view rather than a camera. So to mathematically describe our defined view of the world, we often use the concept of an in-game camera. Intuitively, we define the location of the camera in the world and where it points, and that's going to produce some sort of image, right? So if I was in the real world and I had an actual like video camera and I was moving it around, defining the XYZ location of that camera as well as where that camera is looking at an XYZ location in three-dimensional space, that would produce a view of the world. So similar to real photography, that's going to determine the view of the game world that we see. And that's a very important thing. This is a video called The Challenge of Cameras. It talks about cameras in 3D. This is like a 12-minute video. I'm not going to play that entire video here, but please have a look at that video because it's quite interesting. And it goes into games like, I think Tomb Raider is the main example that they give, and how different camera angles can evoke different emotions or display different information, etc., etc. But I don't want to take up that much of this lecture with that, especially since the link is right there. It does autoplay, so I'm just going to skip that video for now. So, a 3D game camera, if we were doing a 3D game engine, there are many different ways, mathematically, that you can describe a camera. If you think about it, okay, so at some point you're going to have the position of the camera, right? So the camera is, let's say this is the front of the camera. The camera is at a particular XYZ location. And then the camera is also rotated in 3 axes as well. So it can rotate this way, it can rotate this way, it can rotate this way. Some game engines that I've used or graphical systems that I've used have defined it in this way, so position and rotation. Other game systems that I've used that I find a little bit easier sometimes is defining the position where the camera is and the position of the center of where the camera is looking. And so I'm at 0, 0, 0. I want to look at 100, 200, 100, or something like that. So camera views can accomplish many, many different tasks, and they can be implemented many different ways. So over here, for example, on the left, let's try and think about how this camera is implemented. Well, you've got this thing moving around in the game world, right? And that camera doesn't seem to be moving, right? It's just following that thing in the game world. So this camera looks to be like it's in a fixed position, and it's always looking at that entity. Okay, so that's a pretty simple type of camera. Up here, right here, we've got a sort of follow camera. So the camera is always like right behind the shoulder. I mean, you've all seen this in like God of War type games where you're right behind the player as they're moving along. So this is sort of an over-the-shoulder fixed camera position. Over here, we've got a sort of arbitrary game geometry and camera, which is like a VR game. So you're actually wearing a headset, so the camera is following the movements of your head as you are moving around in this game. Up here, here's another example of just a completely fixed camera, right? So some things are happening in the game. It's just a completely fixed camera, almost like a security camera, right? It's just sitting there, like this camera back here. It's just recording whatever it sees. So in 3 dimensions, you get a lot of different camera types that you can use. And you may say, well, okay, that's 3 dimensions, and it does introduce a lot of complexity, but what about 2 dimensions? All we're really doing is like looking at a game world, right? So here's what's happening in our game world. We've got some flat world that we're trying to look at. We've got some camera, and we can think of it this way. This is not actually how it's going to be implemented, but we can think of it this way. If we want the things to be bigger in our game world, so we're going to see less of it, we move the camera toward the game world, right? Because if I move a camera toward something, it's going to be zoomed in. If I want to see more of the game world, things get smaller, I'm going to move the camera away from that thing. So that would be sort of the analogy here, is that you're going to hover the camera over your game world, looking down perpendicular at it, and then you move it away if you want to zoom out, toward if you want to zoom in. But as you'll see, this is accomplished very, very easily. All we're going to do basically in SFML is describe the rectangle of our game world that we actually want to look at. And then that, however big or small that rectangle is, that view is, it's going to be stretched to fit the canvas of our game screen. So it's going to be very easy to accomplish something like this. And you may say, okay, well, that's pretty simple. That's pretty much it, right? And it kind of is in terms of the implementation, right? I'm going to define a rectangle that I want to look at. But the intricacies of 2D cameras come in when you actually want to see the action and follow the player around, okay? So not only that, but 2D game cameras can actually be used for pretty interesting things. So for example, in this one, I'm not sure what this game is. I should have a citation on the screen here. But what happens at the beginning of this clip is you're kind of zoomed in on the player, and then as you get sort of close to this treasure, the camera zooms out to like reveal that treasure, right? So you can use the camera in very, very interesting ways, even in 2D games, where you may think that it's very simple. So here's a video that I'm going to play in its entirety, which shows a bunch of different 2D camera views. And like I said, it's got some music in the background, so I turned it down a lot, so hopefully it's not too loud, but it is kind of nice to have the music there. And then after we see this video, we're going to go through each of the camera types that was in the video just to describe it in a little bit more detail. Okay, so you can't even hear the video at all, so that's fine. So we'll just watch this. There's some text that will appear. Yeah, the volume is up. I don't know why you're not hearing it. You hearing it now? Okay. So that just showcased some of the camera types that there are for 2D games, and just showing you, okay, there's actually a little bit of complexity here. And that's the link to that. It'll be in the slides. So of course I give you the PDFs, so the video won't be in the slides, but I just link to that if you want to go view it on your own. So we're talking about SFML. How would we accomplish some of these things? So that is done via views in SFML. And so in SFML, there's just an SFView class that you can use. And a view is essentially a window into another world. And you're defining how you're looking into that world. So things in our game world can have coordinates that are different from our screen, right? So for example, if we have a 1920 by 1080 window that we're looking at, by default, that view is going to start at 0, 0 and go to 1920, 1080 in the bottom right. So if we have an entity in our game that lives past 1920 or 1080 or before 0, 0, we're not actually seeing that thing in the world, right? We would have to define a view that encapsulates those things. So an SF view is a rectangle representing a 2D camera that you can use to specify which pixels of a game will be drawn to the window. So we could say, hey, I want from 0, 0 to 10,000, 10,000 to be drawn in my game, if you wanted to. So changing a window's view does not alter the underlying entity and sprite positions. It simply changes where in the window that they're drawn, right? So if you really think about it, you could accomplish a camera system in one of two different ways. One would be the way that we're talking about. Keep all of your entity positions where they are in the game world and then move the camera around. But you could also think about fixing the camera and then moving every entity in the game around, right? Which one seems easier to you? I think I'd rather keep all the entities where they're supposed to be. So by changing the view, we can change which part of our game world is actually shown to the player. And so here's some sample code for SF views. And I know this is a bit small here, but let me just go over it real quick. So the view here, if we have a window, we can call window.getView. And window.getView will give us the current view. And by default, the view starts at 0, 0 and goes to width height of the window. We can, so this says here, initialize the view to a rectangle located at 100, 100 with a size of 400 by 200. So we can take that view and we can reset it and we can define this SFML rectangle with the top left position and then the width and the height. We can do lots of cool stuff with this. We can rotate it. So if you want to have some sort of spinning effect when you finish a level or something like that, you can use rotate on the view. There's also a viewport, which we'll talk about in a little bit. Then we can take this view and we can apply it to a window by having window.setView. Then we can render some stuff, and then if we want to, we can set the view back to default. And now, so why would you want to change a view and then change it back to default? Well, if we think about it, let's say that we wanted to have, in our game world, we wanted to draw some view of our game world. The camera may be moving around. But we may want to be drawing some sort of text, for example, maybe the player's hit points or name or something like that. We want that to be fixed in a particular place on the screen rather than in the world, right? So if we just kept the view the same, let's say we just have a centered view on Link as he's walking around in Zelda, right? And we drew the hit points, say, 500 pixels to the left of Link, then let's say we drew the text, the hit points of Link at like 0, 0, right? Then if Link moved away from 0, 0, we would no longer be able to see the hit points because it's living kind of in the game world at 0, 0. So what this does is it sets a view at some point in the game, maybe that's centered at Link, and then it sets it back to the default view, and then it draws the text. And in that way, what happens is you can draw the text at a specific pixel location in the default view, which is on the screen, rather than in the game world. So sometimes you may have to play around with different things like this when you want to do something that's related to the position of the entities in the game world, and then you may want to draw something else that's relative to the window. Okay, so there's different ways to accomplish that. A bunch of the slides that I'm going to show, basically wherever there's a GIF for the rest of these slides, I got it from this blog article. It's a really excellent blog article, and I really hope that you go read it if you're actually interested in 2D games. There's obviously like no exam here, but it's a really, really cool article. So the default view that we've been using so far up to assignment 3, because in assignment 3 you're going to have to follow Mario as he jumps around, or Mega Mario as he jumps around the level. So the default view that we've seen so far, the window is constructed with a default view. And as I said before, the top left of the default view is the game position 0, 0, and the bottom right is width height. And this view doesn't move. And so in assignment 2, for example, and in assignment 1, if the view doesn't move, then our entire game has to fit into those dimensions, right? So it's kind of like an old Pac-Man game where the entire thing is just on the screen. The screen never scrolls, right? And so you're playing the entire game within those coordinates. And so for assignment 2, let's say we had a 720p window, so we had a 1280 in the X and 720 in the Y, then every single entity in our game had to live between those coordinates, between 0, 0 and 1280, and 0 and 1280, and 0 and 720. But that's pretty restrictive as far as games go, right? It's fine for an arcade game like Geometry Wars, but for something where the worlds are bigger, we would want something else. So this works really well for certain arcade-style games or board games, but it's very, very limited. And so as soon as we get into the complexity or size of a game, where let's say we wanted to play Zelda, but we wanted to have a fixed view. Well, the world is so big that we would have to look at the whole world of Zelda, right? And just imagine how small Link would be as we're trying to control him around the thing, right? So we've got to change the view somehow. So as that video showed, there are a number of different ways that we can do that in 2D games, and probably the simplest way is called a position lock. So in a position lock, down here we've got a game. I can't remember the name of all these games, but we're driving this car around in a world. And as you can see, the world is bigger than what we can display all at once. And so as the game designers, we have chosen to display a certain part of that game. So that's a balance between like gameplay. So for example, there are gameplay decisions to be made here, right, as a game designer. For example, if this player is driving around at this speed, they can kind of clear an entire game view in 1 to 2 seconds, right? Let's say they're just driving straight up, then they're probably seeing a new part of the world every second or so. You know what I mean? So like the time it takes them to travel across the entire camera view. So if you've got a game with a bunch of obstacles, for example, let's say there's a ton of lava pits all around here, and you're just going to die if you drive into a lava pit, then you'd probably want to zoom this out a little more to give the player more time to react to upcoming obstacles, right? So there really are game design decisions with how you set the camera, how zoomed in you are, how fast the player moves, etc. So in this type of position lock camera, it's centered on the player's position. And it's best in games where you have smooth overall motion, right? Because if you have extremely jerky motion, even in this game, which you're driving a car, so it's kind of smooth, I'd probably get motion sick after a while playing this game. It's quite jarring after a while. And so it's also best when the character is very small in comparison to the map view. And just keep in mind that any of the techniques that I'm about to show you, you can apply a camera smoothing technique to it. So any of these techniques can employ different camera movement techniques on top of the type of view that it is. So, for example, in this case, this is what I'd call like an auto lock, or it's locked on the target. But we can also think of maybe there's a little delay for the camera to catch up, right? So you move the character and then the camera catches up. And so there are different smoothing techniques where the camera may glide to the target a little bit more smoothly that you can do as well. And so even when you've chosen, okay, I want the camera to just look at the player, there are other parameters there as well, right? Think of maybe like a rubber band. Oh, look, there's a rubber band here. I didn't even plan that, right? Where as I'm moving around the level, maybe this is the camera, so the player's moving, and it's not until a little while after that the camera sort of catches up, right? And so that's a smoothing technique that we can apply. And you're just going to choose which best fits your game, right? So here's an example of Terraria. Terraria has this fixed camera view. There are probably some times in the game where it may zoom in or out for dramatic effect, but for the most part, you've got this really small entity that you're controlling in comparison to the portion of the game world that you're seeing. But you can see here, this works pretty well because it's so small, right? But if you were really zoomed in on that character, this would no longer work. You wouldn't be seeing enough of the world, and you'd be jumping up and down, and it would be quite jarring. Here we've got an example from Super Meat Boy of that type of smoothing motion that I was talking about, right? So that cross here, that's not actually visible in the game, but it's just here for illustrative purposes. And that goes for all the crosshairs that you're going to see in the slides. But here we've got the player is moving the entity in the game, and then the camera has some sort of catch-up mechanic. Maybe it's delayed by like half a second or something like that. And so this adds a really nice like smoothing effect to it. But it doesn't mean that this is better and the other one is worse. This may actually be really annoying in a game like Terraria. I don't know. I've never played Terraria with this type of camera view, right? So, but it really is like a design decision that has to be made. And of course, there are even simpler type of cameras, I guess, where you could just lock the view in one direction and then follow in the other direction. So this is a very old game called Kung Fu. And in this game, just like Mario type games, the camera is going to follow the player in just one axis. So here, this is the x-axis that you're following the player. And so the game is designed so that you don't need to move the camera in the y direction, right? So you can't jump high enough, for example, to make that something that's needed. And then, of course, the the y view will only change once you've gotten through the staircase and gotten to the next level. So the y value really never changes here. However, you can see here that when the player is sort of moving back and forth, this leads to really like jerky movements of the camera, right? So anytime the player moves even a pixel back and forth, the camera is moving to follow the player. Okay, so that's the horizontal camera view. There's also this idea called direction scrolling. So your game, even if it's like a 2D platformer, doesn't necessarily have to be completely horizontal, right? So this is, I think it's Adventure Island over on the left. It's either Adventure Island or Wonder Boy. Wonder Boy was the Sega version of Adventure Island, and I'm not sure which came first, but they use like identical characters, so I'm not sure which game that is. But in this part, it's a horizontal side-scrolling platformer, but on this particular level, it's actually scrolling down and to the right. And I've actually kind of never seen that in another game where this sort of down and to the right scrolling happened. And over here, this is sort of like a 2.5D game where it looks 3D, but you can't actually travel in one of the dimensions. And so this has a sort of directionality scrolling to it as well. And that's not a 2D game, but I just wanted to include it in there. Like all you can do is move left and right, and then it moves you in that sort of depth direction for you. Next, as the video was showing, is this box or trap view. And so what happens is we're going to define a box around the player, and the view moves only if the player attempts to leave the box. And this is very, very useful in games where you have like a lot of jerky back and forth motion. So here, for example, on the bottom in this like gauntlet style game, I don't know the exact name, but oftentimes you're moving back and forth. Like, you saw that Kung Fu game, and as the player was moving back and forth to attack this enemy or attack that enemy, the camera was moving every time. But in games where that happens, maybe you don't want the camera to be moving so much. And so you define this box, and as I'm sure you could all probably figure out, the camera will not move until you're pressing up against that box. That's basically the intuition behind it. So up here, for example, in this game, the player is controlling this vehicle, and the camera is not moving until you've gotten to the top or to the sides of this box. Similarly, right here, you can see when the player moves to the right, only when they reach this side of the box is the camera moving, and then when they fall, there's a little portion of the fall where the camera doesn't move, and then as soon as it hits the bottom there, that's when it does start moving. And so this is like, it's really, I think this is a really good camera system, because you can have lots of interesting gameplay mechanics going on without the camera moving because of this box trap. But then only when you do, okay, now I'm going to travel in the game, will I actually start moving the camera. But the interesting thing is where you place the box, right? So in this game, the box is centered around the center of the screen, and you can see that that creates, again, some sort of interesting gameplay mechanic. And so as a designer, you have to really think about this, because this game is centered, I think, a lot more on vertical than horizontal movement. So down here, the point of this game is sort of move to the right, okay? And so you may start on top and then move down and to the right. And so if you're moving down and to the right, you sort of want to give more leeway with your box trap for the right and down directions. So for example here, in this game, it's not until you're right here that the camera moves forward. So if you're moving to the right, you only have this much distance to see enemies that are coming, right? Versus in this game, you get to the middle of the screen and that's when it starts scrolling. So you can see these enemies with more time, right? So your positioning of the box trap determines how much time you have to see enemies and react to them. And so it really is an important decision. It's not just, okay, I'm going to put it in the middle all the time. You may actually want to do something different. Here's a video from the game Fez, and this is like one of the most interesting cameras I've ever seen in a game. And so it's sort of like a 2D side-scrolling game in which you can switch the direction in the 3D world that you're looking at. And there's some puzzles based on this, but I just wanted to show that there is a box trap being implemented in this game. However, there's no top to that box. Okay? There is a platform, and I'll talk about this in a bit. This is called position snapping, where the bottom of it tries to come to you rather than you moving it by going to that. So this is actually a combination of a box trap in the X and Y direction and position snapping in the Y direction. And so I'll have more examples of that in a bit. Here we go. So position snapping, it's going to follow the character in one direction. So here, what we have is a combination of two camera systems. So this is a bit like what we just saw in Fez, but Fez had a box trap rather than following. So right here, we see that there is a horizontal line right here and a vertical line. The vertical line indicates that the camera is following the player in the horizontal direction. So it's always centered on the player. Well, not quite centered. It's to the left a little bit. And that's for the same reason as before, because we want the player's going to be moving to the right to finish most levels, so we want to give them a bit more time to see enemies. But then what happens is, as the player deviates in the Y direction, this platform catches up slowly to the player. Okay? So that's called position snapping, and it's called snapping because usually it's a bit quicker than this, so it snaps right up to the player. And so you snap the position if the character changes in the other axis that is not being followed. And this gives a bit of smoother overall camera movement, right? Because if every time we jumped, the camera jumped, that's a bit of a quick movement. And so the speed of your movement in a given axis will probably also help determine the camera system that you use for that game. So this was position snapping, where no matter where the player is on a platform or not, that horizontal part of the camera, or the camera is going to follow vertically with that horizontal line to match the feet. But there's also something called platform snapping. And depending on your game, you may want to choose one or the other. And so this is like position snapping, but it occurs based on level geometry. Okay? So when you determine that your character is on flat ground, then we determine, okay, that's like a platform. And so here in Super Mario World, in this particular level, when you're jumping up vertically, the camera doesn't move until you have made significant progress to the next platform. Okay? And actually, it's kind of interesting because if you can fly on this level, if you can get enough speed with the cape to actually fly up, then you can fly up, and if you haven't landed, you'll actually be off the screen because the camera hasn't updated. So if you watch some speedrunners in this game, there's some times where they'll be completely off the screen because the camera hasn't caught up to them yet. And so here's another example of platform snapping, but in a game that has, I guess, less well-defined platforms. And so in this one, the implementation is pretty simple. When you're detecting that you're going on flat ground, that is when you would update the camera's position. There are also this idea of camera zones, which are kind of like a box trap, but not exactly like a box trap, where something happens based on the zone. Okay, so box traps are a very specific thing where the camera is going to definitely move if you are touching the side of the box trap. But here, in the original Super Mario Brothers, you have a completely different thing that's happening with that. So, kind of like a box trap here, this rightmost line, this is when Mario walks to the right and hits this line, the camera updates. But when Mario, in this particular game, can't move back to the left, okay? So when Mario moves to the left of this line, of the middle line, then the camera doesn't move. But this second line here, it's a bit more nuanced, where the camera starts to move when Mario reaches that line, but Mario is not maybe up to speed yet. Okay? So it'll start to move when Mario reaches the first line, but then follow once it reaches the second line. So you can think of so many different things that you could do with arbitrary camera physics, if that's what you want to call it in these situations. Metroid had camera zones as well. These are more like box traps, but not exactly box traps, where you can see that as we move to the left or right, this is moving, but I'm not sure what the extra mechanic here is. But these are acting quite like box traps. In Super Mario World, for the platforming, the regular level sections where you're not doing a lot of vertical movement. So here you can see that in Super Mario World, there's many different camera systems, right? Because we just saw one example that had platform snapping, but this one does not have platform snapping, right? There is no camera movement in the Y direction in this particular section of the level. So you could have cameras defined by parts of the level as well. But here what we have is this is kind of hard to define, but you can kind of see what's happening here. And it depends on which way Mario is facing. So before I said that you want to position a box trap based on where you want like sort of that leeway in the vision. So the box trap in the gauntlet example was saying, okay, most of this level is moving to the right, therefore I place my box trap to the left so I can see more to the right. But what's happening here is I want to be able to give leeway in both the left and the right directions, which is not necessarily possible with just a box trap. So what happens is, if Mario is moving to the right, then the camera is acting as a box trap in this second line, right? But if Mario is moving to the left, then it only updates on this line. And the camera only starts moving on a direction switch when Mario reaches these dashed lines. So it's a really interesting camera system. I really love the camera system in Super Mario World. It's very intuitive, it's very smooth, and it just like feels right to me. But you can see that this is actually quite involved, right? There's a lot of interesting things going on here, and it's all related to the gameplay mechanics that you want to highlight in your game. Here is another example where we have this sort of, what did they call it? With the echo example in the games, like it was either look ahead or follow camera, I can't remember. But essentially what you have are these positions in the game where if I'm moving to the left or to the right, then the camera is going to snap at these positions. And so this game, oh, I can't remember the name of this game. My uncle actually owns this arcade cabinet. So he'd be upset with me if I couldn't remember it. But essentially in this game, your ship is moving very fast through the environment. And so if you're moving, and throughout the game, you have to move to the left, to the right. It's like a whole planet that you're kind of exploring. And so if you're moving to the left, then the camera will, well, you can see what's happening, right? You switch from left to right, and the camera is going to switch to be following you from either the right-hand side if you're moving to the left, or the left-hand side if you're moving to the right. And what that does is, because you're moving so fast, it gives you a bunch of screen in the direction that you're facing. And similarly, down here, this is a combination of this system with a snapping vertical system. And so up here, it's just horizontal camera movement. Here, it's vertical as well, with a really slow vertical snapping system. There's also zooming and focusing that you can do. So over here on the left in this Yoshi game, there may be something that's happened in the game that is off of the screen that you want to somehow communicate to the user. Like, for example, this thing that's floating down here, or maybe Bowser is too far away, or, as I'm about to show in the next slide, in a fighting game, when you move farther apart, you want the camera to zoom out. You don't want one person to be off of the screen. And so you can zoom in and out to give some gameplay focus that you want as well. Over here, I'm not sure what's going on here, but there's a whole bunch of crazy stuff happening with the camera, where you're sort of giving leeway with the camera in some sections when you're moving fast, and then in some sections you want it to be centered on the player. So completely arbitrary stuff going on here. I couldn't even begin to describe it. Maybe it's in that blog article. Also, you could think of a camera window. And so this camera window, as players move beyond these lines, so to the left and right, then in a fighting game, you can be very, very close to your opponent, or you can be further away from your opponent. And depending on the game, the camera may actually zoom out or zoom in when you get further away or when you get closer. I remember in the old Virtua Fighter games, if you got really far away from your opponent, you'd be like this tiny speck on the screen. It was actually kind of strange. So here, as you move to the left or right and you hit these boundaries, that's when the camera starts scrolling. And then in some fighting games, it would actually zoom out when you get further away. And that's because, you've got to have both characters visible at all times in multiplayer games like this. Then you can actually put in special effects with your camera, right? So these special effects, like camera shake, that's just moving the camera view around. So you can think of how you might implement something like this, and you can, this really large enemy, or an explosion goes off, you can shake the camera. Okay. Here's another type of view. This is part of the map from the original Legend of Zelda, and it's going to be the inspiration for our assignment 4. And as you can see, it's pretty tiny, right? Well, the world is big, but if you were trying to move Link around in this world, it would just be too tiny. You wouldn't be able to see any of the gameplay. And so in this game, the game was broken down into rooms, essentially. So rooms or a grid, if you want to look at it either way. So for example, at some point of the game, you are in this area, and so this is all that you can see. And so what happens is the camera, when you enter this area, switches so that it shows that entire area, and while you're in that area, the camera doesn't move. But then if you move to another area, then the camera goes to that location, and while you're inside that area, it doesn't move. And for this game, this is approximately the size of the camera that was being used, but we could make that as arbitrarily large or small as we want. But, of course, for assignment 4, we're going to have a fixed size that we're using for our rooms. So I showed a little example of this, but let's go into more of sort of notes for your assignment. So a view can be constructed in one of two ways. So you can construct it with a float rect. So a float rect has a top left x, a top left y, and a width and a height. Or you can specify it in a different way, which is by specifying. Okay, so that's the rectangle way, where you say, I want to look at this rectangle of the world. But another way, which is very convenient sometimes, is just to say, here's where I want the center of the camera to be. So for example, if you did want to do something like a follow camera, and all you could do is create this rectangle, then you would have to do the math of like, okay, where is the top left and what is the width and the height if I want Mario to be in the middle of the screen, blah, blah, blah. But here, SFML just allows you to, this second constructor lets you pass in a center X and a center Y and a width height, and then that would just let you do it. And so that means that the same resulting view can be accomplished in multiple ways. So if we did have a rectangle with a top left of x, y, and a width and a height, then we could also specify this by using this SF vector 2f method by specifying what is the actual center and the width and the height. Okay, so any view that we want to actually specify, there are two different constructors. And so this doesn't make a new thing possible. It's just that you may want to use one of these constructors in one case if you're following something around, and maybe not use it in another case, like where you're trying to just show a room, for example. So using the top left or center method may be more convenient based on the game that you're making. So here, for example, is a rectangle that we may want to define. And so in assignment 4, this is actually what we will be doing, is we'll have a rectangle which is at x, y, that's the top left, and then we have a width and a height, and that's just going to determine what we see in the game. Very specifically, in our assignment, this is the type of room that we're going to be looking at, and I'll give you the exact dimensions of that room. And so x, y is in the top left, width, height again, but the same thing could be accomplished by defining the center position and giving the width height. So that's just a little diagram showing you what's going on. And we will actually have two camera views in that game. One is the room view, and then you're going to hit, I think it's like the Y key or something, and when you hit that key, the camera is going to switch to actually following Link around. Okay, so you can use that second method where you define a center point for that camera view if you find that easier to do. So views can be set after a window is constructed, and you can say view.reset, as I showed before. You can say view.setCenter, you can say view.setSize, etc. Views can be moved, so I can say move, and what this will do is it will keep the same width and height, but it will change the top left corner. Right? So if I want to move by 100, 100, I don't need to say, okay, get the x and the y and add 100 and make a new view. I can just say view.move. And so this changes the rectangle position to this, and then the view can be zoomed in or out toward the center. Just be aware that as far as I can remember, this may not be the case, but I'm like 95% sure it's the case, that you can't just say window.view.setCenter. Because the window.getView, that returns a copy of the view. And so what you have to do is say window, give me your view, and then you edit that view, and then you say window.setView with the edited version. Okay, so you have to kind of get the view, modify it, and then set the window view. And so if you want to zoom, view.zoom, and if it's less than 1, it gets closer. If it's greater than 1, it gets further away. View rotation, so you can rotate the camera as well. Just imagine trying to play this game. And it's kind of interesting because the game coordinates all stay the same. It's just the view that gets rotated. So here, if I was actually controlling Link and moving Link to the right, then Link would move up on this slant on my screen, right? Because it's not rotating the world. It's just rotating the camera's view of the world. So this could be used for interesting bonus marks on the project, for example, or the assignment. So the controls are the same, just the views, just the view changes. The second thing that we have, so we have views, and then we have viewports. And so if a view defines which part of the game world will be seen, then a viewport defines where on the window we will draw the world. Okay? So for example, you could say, draw only on the left-hand side of the screen, or draw a mini-map icon up in the top right. And so by default, the default view is the contents of the entire window. And so the viewport is not defined in terms of pixels, but instead as a ratio of the window size. So if you define a viewport, so you can say view.setViewport, and then you give it a rectangle, x and y are a ratio of the window, top and left, and then width and height are a ratio of the window size. What do I mean by ratio? Well, here's what I mean by ratio. So here, this right here, this is the x, and this is the y. And up here you can see that we've defined the top left of the viewport as a ratio of the screen size. So this says 0.25, 0.25. So this means to start drawing the view 1/4 of the way over and 1/4 of the way down in the window. And then this is the width and the height. So the width of this viewport is half of the window size, and the height of the viewport is half of the window size. Okay? So viewports are defined in these ratios of the window size, which actually makes it much easier, in my opinion. So viewports can be used to create really interesting or useful gameplay. So for example, if you're making a racing game, you can have 2-player split screen, right? For free. You just have 2 different views that you're drawing with 2 different viewports. So for example, if you want 2-player split screen in your game, you can absolutely have that. So think about local multiplayer. I don't know if any of you are old enough to remember local multiplayer, but you used to be able to play against each other without having an internet connection. So anyway, here you could have a player 1 view and a player 2 view. And so the player 1's viewport would start at 0, 0, right, in the top left of the screen, but then it would only occupy the left half of the screen, but the whole width, the whole height. And then the player 2 would start halfway over in the x direction, but all the way up is 0 in the y, and then be half. So what we would get here is the following, right? You could be over here following one player and over here following another player on the same screen. So again, right here, oops, I deleted my laser pointer. So the first player would start at 0 in the x and 0 in the y, and they would go to 1/2 of the x as the width and 1 as the height. And then the second player starts at 0.5 in the x direction, 0 in the y direction, and they would go half of the screen in the x direction and all of the screen in the y direction. And you could have 4 players, or 8 players, or 16 players, or however many you want, as long as your computer can handle the math that goes behind it, right? Or you could create a mini-map view if you wanted to, right? So maybe I have my game view, which is 0, 0, 1, 1, so it's the whole screen, but then on top of that, I could draw a viewport which is like this tiny mini-map. So here, for example, this is going to be over at 0.75 in the x, 0 in the y, and maybe it's 1/4 of the screen. So this is what that might look like, right? Where I start 0.75 over, and then go 0.25 and 0.25, and now what I have is whatever I define, maybe the view of that viewport is the entire game map, right? And I draw like a circle where I am in that game map. So that's how you could do a mini-map for your game. So viewports can be used, oh, I already did that. Yeah. So 2-player split screen, in-game mini-map, maybe you have a rear view mirror, something like this. Or maybe you could have an enemy perspective, right? Like you start showing the world from the boss's point of view. I don't know. Like there's a lot of interesting things that you could do for the project using views and viewports if you really wanted to. And so you don't have to do something boring. You could get bonus marks for having a really cool Really cool view system. And so there's many different ways that we could actually take our game engine architecture and then implement the code for this, right? Like, so I've showed you the code, but we also have this nice architecture that we're trying to follow. So how would you actually implement these camera types? So there's two main ways that you could do that. One of them would be to implement camera types inside an ECS system with an enum. So basically an enum is just like an integer, so you'd have a bunch of options for your camera. So if camera equals this, then do this thing. If camera equals this, then do this thing. Or we could implement like a camera class that's passed into the game engine, and we could change the camera class. This way is more typically how things are done in a 3D game engine, where you have a camera, it has a position, the camera has certain properties, the camera has the zoom factor, it's the thing that it's looking at, whether it's orthographic, whether it's projection, all these different types of things. So what we could do in our game, and there will be something like this in our game for assignment 4, and hopefully for the project as well, where we're going to have a bunch of different camera types, right? So I could say follow in the X, follow in the Y, maybe have a box type, maybe a Zelda room, maybe a default camera view. And then down here, we will actually have a camera system in our game engine. So we just have a system that says, hey, if the camera type is this, then implement and update the view for that. If the camera type is this, implement and update the view for that. And so this is the way we're going to be doing it in this course, because we do want that ECS and S is the systems, of course. But you can think of a way in which we might have, like, here's the game engine, here's our camera type, and then we do the updating inside the camera class. But this is not the pure ECS way of doing things in this particular class, so we're going to be using the system for that. Okay, so that is cameras and views in a nutshell. But for your project, you have to implement some sort of parallax effect. And so I'm going to play this camera now to show you what parallax is. But in essence, the entire idea behind parallax is that if we only have 2 dimensions, there's a real dimension of the physical world that we're missing. And so what parallax is typically used for is to introduce a differential in movement between certain parts of the game, typically background or foreground elements of the game, to fake some sort of 3D, right? And parallax was used very extensively in like old Disney movies to indicate depth as well. Because if you think about it, an animated movie, a 2D movie, has the same problem that we have. We have to define camera views. We have to move the camera around. We may want to indicate, okay, there's like a depth to this forest in the background, etc. And so that's what this video is, and I'll play this video now with the time that we have remaining.